Throughout the centuries, human beings have looked at the stars with astonishment, wonder, and curiosity, wondering what could be the origin of such magnificence and the nature of its evolution. These questions have been the subject of religious, philosophical, and scientific debate and disquisition since the earliest times of human history. All the greatest minds of the scientific world have asked themselves these questions, giving different answers and proposing theories sometimes conflicting with each other. Among these, one of the most famous, as well as the one currently accepted, is undoubtedly the Big Bang Theory. However, its fame is often accompanied by deep misunderstandings and false conceptions about its real meaning and scope, even by so-called experts in the field. For example, one of the most common errors about the Big Bang Theory is to believe that it is able to describe the origin of the universe. In fact, it represents an attempt to explain how it has evolved from a presumed initial event, characterized by conditions of density and temperature extremely high, but it's not able to explain how it really began the process of creation of the universe, or what actually could have existed before that event, or if, again, there can be something outside the universe as we know it today. Another gross misunderstanding is that, according to which the Big Bang is associated with some kind of giant explosion. The theory, in fact, proposes the purpose, unfortunately not fully achieved as we shall see later, to describe the hypothesized expansion of the universe from a primordial state up to the size currently estimated on the basis of astronomical and astrophysical observations. Although most of the formulations of the theory describe an incredibly fast expansion of space, potentially greater than that of light, it's not possible to consider this process as an explosion in the usual sense of the term. Apart from this, it is always good to remember that, however magnificent, this physical mathematical construction is still a theory, perfectible, but also subject to possible refutations. Look, this is the cosmos. Each of these tiny lights represents an entire galaxy. Each is composed of hundreds of billions of stars. In shaping the universe, gravity builds a web-like structure of filaments that bind galaxies and galaxy clusters together along invisible bridges of gas and dark matter, hundreds of millions of light years long. Billions of galaxies form a web that permeates the entire universe and expands in all directions. And among all those galaxies, there's one in particular, spiral-shaped. Inside it, there is a bright star, a star like many others, around which 8 planets orbit, and one of them is inhabited by an animal species that only recently began to understand something of what surrounds it, making more discoveries in the last century than in its entire previous history. Only since a century ago, in fact, we humans know that everything that exists is formed by matter recycled from the stars, huge atomic furnaces that burn hydrogen and convert it into heavier and heavier elements, without which nothing we see could exist. But where do stars come from? Who created them? And here, the eternal question arises. Our eternal need to get to a first cause, to the beginning of everything, and even beyond. The fact is, it baffles us to think that the entire universe, all galaxies, time, space, and forces of nature themselves materialized out of nothing. But we must choose to be on the side of the scientific method and only talk about what is possible to prove. Our goal must be to understand how the universe works and how it exists. And the only way to do that is to entrust our desire for answers to the only thing that can bring us information from the cosmos: light. The light that comes from stars, nebulae, and galaxies hides a treasure trove of information, without which we could never have even imagined their real nature. The invention of the spectroscope and the consequent birth of spectroscopy in the 1800s opened the door to modern astrophysics. The bright spots we observe on the vault of heaven are probably only an infinitesimal part of what exists, but they are a sufficient trace to understand the past, the present, and perhaps even the future of the universe. Seen from the Earth, all the galaxies we talked about before, that is those that form the fabric of the universe, filling it with a dense web of filaments, appear a slight red color, almost as if we were looking through colored lenses. Just this detail reveals how the universe was born. The light, we said, contains a lot of information that must be decoded, and one of these concerns the movement in space of the object we are observing. The light waves, in fact, undergo a shift towards red or blue, depending on whether the source is moving away from us or approaching us. The phenomenon is commonly known as the Doppler effect, and the red color indicates that the galaxies are currently moving away from each other. The entire universe is in fact expanding in all directions, and with a speed well defined by the famous Hubble's law. Realizing this was like winning the lottery for cosmologists. They wanted to find out when the expansion had begun. Well, the further back you go in time, the closer the galaxies had to be to each other. Therefore, it would have been enough to run the film backward to go back in time when all the matter had to be concentrated in a single point. Thus, it was discovered that about 13,700,000,000 years ago, what we know today as the universe must have occupied a dimensionless region, a region that was given the name of Singularity, to emphasize the peculiarity of a situation outside any logic of physics, characterized by infinite values of temperature and density. You could imagine this singularity as a huge black hole, but here hides one of the biggest mistakes in understanding the universe. You should not think that all matter in the universe was compressed in a point of infinite mass. This would be a singularity very similar to that of a black hole, held together by the gravity of the matter. The singularity of the Big Bang was instead only made of energy. There was not even an ounce of matter, and not even gravitational force, as the four fundamental forces, electromagnetic, weak nuclear, strong nuclear, and gravity, were perhaps still unified into one fundamental force. How long had this singularity existed? What generated it? These questions remain unanswered, just as the uncertainty about whether this entity really existed in the terms in which we have described. However, then something happened, and the singularity expanded with a tremendous emission of radiation. In an infinitesimal fraction of a second, the universe went from the size of an atom to the size of an orange. The universe began to exist, expanding and unfolding. It became larger and gradually began to cool. In just 100 seconds, it became as large as our solar system, with an extension of billions of kilometers. During this process, the massive energy began to cool and create matter in the form of billions of subatomic particles, the first nuclei of existence itself. About half of these particles were composed of matter, the same substance of which we are made and everything around us. The other half was formed by the opposite of matter, a substance called antimatter. And when matter and antimatter meet, they destroy each other in a process called annihilation. The birth of the universe has therefore involved a huge loss of matter and energy. Fortunately, the amount of matter was slightly greater than the amount of antimatter, so the matter survived, even if only thanks to a particle in a billion. And it was up to this infinitesimal residue to give origin to the universe we know today. With time, the primordial cosmic plasma, initially homogeneous, turbulent, and very hot, began to form small eddies and thickenings. About 100,000th of a second after the Big Bang, the temperature was sufficiently lowered, reaching about 10,000 billion degrees, more or less a million times higher than the temperature found inside the Sun, for quarks to aggregate in groups of 3, forming protons and neutrons. About 100th of a second later, From this plasma of cooling particles coagulated the nuclei of some of the lightest elements on the periodic table, hydrogen and helium. During the next 3 minutes, while the universe was gradually cooling down to the temperature of 1 billion degrees, it continued to form a large majority of hydrogen and helium nuclei, along with a few traces of deuterium, heavy hydrogen, and lithium. This lapse of time is known under the name of the period of primordial nuclear synthesis. Already in the first 10 minutes, the cosmos reached a diameter of light years, then continued to expand and cool for about 300,000 years. But when the temperature lowered to reach a few thousand degrees, electrons, that before were agitated wildly, slowed down to the point that atomic nuclei, mostly hydrogen and helium, were able to capture them, forming the first electrically neutral atoms. It was a crucial moment. From that moment on, the universe became, as a whole, transparent. Before electrons were captured by atomic nuclei, in fact, the universe was a dense plasma of charged particles. Photons, which only interact with electrically charged objects, were incessantly hampered in their motion by this soup of charged particles and could not travel even the smallest distance without being absorbed or deflected. This made the universe completely opaque, as in a morning of thick fog. But when negatively charged electrons began to orbit around positively charged nuclei, producing electrically neutral atoms, the obstacles of electric charges disappeared and the thick fog thinned. From that moment on, the photons that emerged from the Big Bang could progenate freely, and the universe gradually became visible in all its extensions. As soon as the radiation was free, its pressure, which had kept the matter in a fluid state, became insufficient to counteract the gravitational attraction. Matter began to clump. The process of the formation of stars and galaxies began. Our era began, the era of matter. And there were nebulae, clusters, and galaxies, and quasars, and first-generation stars. A process not yet well understood, clouds of hydrogen and helium thickened, forming immense structures in a space that kept growing all around. Perhaps 5 billion years were enough to have structures like the ones we observe now in our telescopes. The first stars were ignited. Gigantic blue stars, immense nuclear furnaces where hydrogen was transformed into helium, energy, and light. But nuclear fuel is not inexhaustible. Once the furnace is turned off, the tremendous and inexorable grip of gravity tightens the matter and brings it to enormous temperatures, density, and pressure. In this crucible, the heavy atoms are created: iron and gold and lead and uranium, those elements that were not created in the beginning. And stars explode, and from their ashes, new stars are born. First-generation blue giants turn into supernovae, exploding with glory. Their splendor equals that of the galaxies. Their ashes, seething gas, swirl in space, forming new rotating nebulae, rich in all the 100 chemical elements, while their nucleus collapses, forming neutron stars and black holes. From the nebulae, slowly, by gravitational attraction, new stars are formed. Our stars, white, gold, red, and giant gas planets and small rock planets rotate around these second-generation suns. In one of these nebulae, the result of a stellar explosion 5 billion years ago, our sun was preparing to be born. So where do we come from? Well, it seems that science has provided a rather detailed answer. We can also choose at will one of the topical moments. We are the children of the Singularity, born from the flash of light that freed matter, forged the heart of the stars, conceived in the agonizing agony of supernovae. It is truly extraordinary that in less than 4 centuries of scientific evolution, we have come to answer such ancient and fundamental questions. We know how and when the universe was born, how it is structured, how it works, and, with some uncertainties, how it will end. What is left to discover? Very little, few details. No more mysteries, no more surprises. But is it really so? It is fashionable to talk about the end of science, an end caused by too much success of science itself. It's not a novelty. At the end of the last century, after the definitive theoretical arrangement of mechanics and thermodynamics, after the elegant and brilliant Maxwellian synthesis of electromagnetism, famous scientists were saying the same thing. Great physicists were inventing brilliant students to change the field of study since physics was practically completed. Yet within a few years, the revolutions of relativity and especially quantum mechanics shook from the foundations the solid building of what is now known as classic physics. Nature has many more surprises than we can imagine.